So I hope everybody can hear me. I want to welcome you to this rapid interactive session. The session number is WeA02. My name is Cam Liang from the University of Utah, and I've got co-chair Professor Santosh Devasya from the University of Washington. And also you see Professor Alex Dowling from University of Notre Dame. He's joining us here as one of our panelists for the keynote talk to start off this session. Just a few reminders and just a little bit of an intro to how this is going to work. So this rapid interactive session will contain essentially 23 talks from 23 papers. With somewhat of a focused emphasis on control of energy and automotive systems. So the way the rapid interactive session works is this first block, starting now until roughly about, say, almost 11 o'clock, will be a keynote talk where Professor Dowling will present his work for about 12 to 13 minutes, and then we'll field some questions from him for about 5 minutes. And during his presentation, you can actually use the Q&A feature, and he's going to take your questions directly in real time as he gives his talk. So that's a nice feature of this webinar setup. And then after his talk, we'll do a quick Q&A followed by 3-minute talks that have been pre-recorded and all compiled together. So hopefully everything will play smooth and seamless. And these talks will be played back to back. And unfortunately, there will be no Q&A in this particular session for those talks. After those talks, I'm going to invite everybody to step out of this room and then go find the individual Zoom rooms for those for all the talks and visit the authors that are going to be in the rooms sharing, again, either their videos or additional slides. And that will allow you to interact with the speakers in a more intimate setting. And I encourage you to visit the collection of talks. And again, we've got 2 rapid fire interactive sessions going on in parallel. There's WeA01 and WeA02. And so there's a total of, I think, 44 talks in this first 2-hour block. All right, so the other thing is Professor Devasya is going to be sending out through the chat several links for you to vote on the People's Choice for the RI presentations for this session. And then also there's the Hugo Schuck Award. There's some details that'll be sent out, and he'll periodically send that out through the chat. And that's it in terms of all my kind of stuff that I need to tell you. So it is my pleasure to introduce Professor Dowling from the University of Notre Dame. The keynote is, the title of it is Making Money in Energy Markets. He'll talk for the next 12 to 15 minutes here. And feel free to use the Q&A feature to ask him questions in real time. And I'll go ahead and play the video. Thank you.
Hello, my name is Alex Dowling. I'm an assistant professor at the University of Notre Dame. Today I'll be talking about how to make money in energy markets, specifically how to use probabilistic forecasting and stochastic programming to optimize participation of energy systems or resources in wholesale markets, and also to understand the interaction between resources in said markets. This is joint work with Qian Gao, my graduate student, and is part of the Institute for the Design of Advanced Energy Systems. Electric markets in the US have decisions that span 12 orders of magnitude, from kind of control decisions at the millisecond scale all the way to investment decisions at the decade scale. And as part of the IDEAS project, we want to be able to couple and build simulation capabilities that span this scale. This is especially important as there's more and more intermittent resources, as these cause more and more variability and volatility in the markets, and are causing prevailing paradigms like levelized cost of electricity that are really based in steady state or baseline power production to become obsolete. And what's happening is the economics of a new technology heavily depend on the market. We want to be able to capture that and understand that. This talk's going to focus on real-time and day-ahead markets, which is at this time scale here, from like minutes to a day. So first I'll give some background, then I'll compare bidding and self-scheduling paradigms, and then I'll talk about co-simulation to understand these resource grid interactions. So Energy markets are hierarchical. In California, there's 3 levels. There's a day-ahead market, which sets hourly prices, and a 15-minute market, which sets 15-minute and 5-minute prices. If this wasn't complicated enough, these prices are actually set in spatially distributed. So here's a snapshot of prices in California. Each dot is a node. Prices vary by node. There's about 8,000 nodes in this picture. We can see from this time series that at the blue line, which is the day-ahead market, that's fairly periodic. There's a lot of volatility in the red and the green, which are the real-time market. When a resource decides to participate in the market, there's a lot of options. One could transact energy. So this is either is consuming or a generator, and that's the day-ahead market and the real-time market. Or there's also these reserves and regulation ancillary services. In general, the faster the time scale, the more economic opportunity. For the rest of this talk, we'll just focus on the energy markets. There's a lot of literature that also considers energy-intensive processes. So one is scheduling with time-varying prices. This is about a 20-year-old problem. And there's, the consensus of the literature is there's about a 5 to 20% increase in revenue or decrease in cost over steady-state operation. Well, there's a lot of recent literature in the last 5 years then looking at extending this to ancillary services, and they find about 20% or more opportunities going beyond just energy markets. And finally, I want to point out that Alcoa actually does this with their aluminum smelters, and they've publicly said participating in markets has reduced their energy costs by 10%. So hopefully you're convinced that there's a lot of opportunities coming from these multi-scale hierarchical energy markets, and this can really motivate a lot of good control research questions. Today I'm going to talk about uncertainty and assumptions, especially this price taker assumption, which is that a resource is so small that its actions don't influence the market. And we'll talk about how to assess that. So in this first case study, we want to compare bidding and self-schedule, talk about how to formulate these, and talk about which approach is better. So before we can get into that, we kind of need to understand the steps for participating in the market. So it starts with a resource in the market making a forecast. And this is forecasting the price in the market or the load. So the market will forecast load and renewables. A resource then needs to ask if they're going to be self-schedule or bidding. I'll talk about both of these in a minute. This is either going to result in a schedule where the resource is saying, I'm going to use this much power every hour, or a bid, which contains cost information. The market then clears by taking all of these bids or all of these self-schedules from every node that was shown in that California picture, and then trying to minimize the overall system cost subject to constraints for both individual resources and constraints for the overall system, so like the transmission network. This then gives hourly schedules or set points for every resource and locational prices. Each resource then needs to track their signal from the market, and then the actual plant outputs are then observed by the market, and that allows for payment to be calculated and the time step advances. Each cycle through this loop is nominally 1 hour. And I want to point out when I say resource, this is both thermal generators, some large-scale renewables, some grid-scale storage. So it's a very general definition. For the probabilistic forecasting, which is step 1, we've done some work with some Gaussian process models. These are nice because they have a predictive distribution, and we're also going to compare different ways of sampling these. So Monte Carlo sampling, which is kind of like a statistically well-defined sample, and then some other techniques that care less about statistical accuracy and more about just getting spread in these scenarios. So with these forecasts, a resource can either self-schedule or can bid. In the self-scheduling paradigm, the resource has these forecasts and then says, how should I operate to get the best revenue with this forecast for uncertainty? And then the resource just takes the market price. And this can be formulated as a multi-stage stochastic program. In contrast, in bidding, the resource actually tells the grid about its cost through a bid curve that looks like this. So it shows power here versus price. So this is how much power a generator is willing to produce as the price changes. And this you can calculate with a 2-stage stochastic program. So notice that each time series forecast for price here can correspond with a scenario, and you get one bid curve for every time step, or one bid curve for every hour. The optimization problems are shown here. The goal is to maximize the expected value of revenue minus costs. which can be approximated with scenarios. This is subject to market rules and some integer decisions and start down and shutdown constraints, dynamics, ramping, and bounds. I want to just point out non-anticipativity. For self-schedule, you could maybe enforce that the first 4 hours, the control actions across all schedules need to be the same. For the bidding, non-anticipativity enforces that this is increasing. So now I want to talk about market clearing. And we're actually going to propose here a way to do this with historical price data, because the data needed to simulate a real grid like all of California, that's protected data that is difficult to get access to. So the way that this works is we have as inputs bid curve and these historical prices. The first step is to then take the bid curve, look up the historical price. That gives these bounds on power. Those then enter into an optimization problem. The way to interpret this market clearing is what is the best schedule that maximizes revenue for the generator, but is constrained by their bid curve and the historical prices. So it's kind of like an upper bound, estimating upper bound on revenue, but using bidding. So let's see this in action, and we look at a combined cycle gas turbine example taken from literature. Here I'm going to compare four ways of interacting in the market. First is perfect information. Blue here are power outputs. The solid black, or the dashed black line, is the actual market prices. This is the best the resource could do, but this requires knowledge of the future. Static bidding is a bid curve that's just derived from steady state costs. Contour bidding, this is doing bidding, but with these contour samples, which are more spread out. And then Monte Carlo self-schedule is taking these Monte Carlo samples and doing self-schedule. But here, big takeaway message here is that there's a big error between the red line, which is the price forecast mean, and the actual price. And with this error, the Monte Carlo, the self-schedule says, the price is going to be so low, it's not worth my while, and the generator isn't turned on. But with bidding, it is turned on. And the idea is with self-schedule, the resource internalizes uncertainty. But with bidding, the resource communicates kind of like a recourse policy to the market. So bidding is more robust to price uncertainty. We also see this in rolling horizon simulation results. We have a year of data from California market. And shown here with bidding, you can get 99% of the perfect information revenue. With self-schedule, we could only get 78%. So these results really show that if you're going to think about assessing the economics of an energy system with historical data, we'd really under uncertainty, we'd really advocate for using bidding. Next, we want to understand how do you capture these interactions between resources and grids in a real electric market. And here we're going to propose a more complicated workflow where there's two loops. One is for the day-ahead market. One captures the real-time market. Stars are optimization problems that are solved by the resource. Pentagons are optimization problems solved by the grid. And we're going to use Prescient, which is an open source cost production model. Prescient was very carefully designed to closely mimic real energy markets in the US. And we're going to use the RTS GMLC open source data set that roughly mimics the Southwest US. We're going to take one generator in the RTS GMLC test case, and now we're going to optimize its bidding. So the results shown here, on the left, we have 4 bidding curves. The blue is the static curve, and then we have a bidding curve for 5 p.m., 6 p.m., and 7 p.m. And the takeaway message is these bidding curves are very similar. If we inspect these schedules, we see that the schedules are very similar. But when we apply this in a rolling horizon framework over 4 days to kind of demonstrate this workflow, we see there's actually a 4% improvement in the optimal bidding. And this comes from an unexpected source. This comes because the optimized bidding is actually influencing the market prices. So shown here is a histogram of prices with static bidding. Shown here is the same histogram with optimal bidding. And we see we go from 2 to 3 hours where the price spikes up to its upper bound in Prescient. And what's happening with this extra price spike here is it's shifting the median and it's shifting the mean. And this big shift in the mean by about a factor of 10, that's what's driving that 4% increase in revenue. So our hypothesis is these small perturbations in the bid curve are causing the dispatch schedules to be slightly different. And this is causing some transmission constraint to be active, which is causing these price spikes. So the takeaway message is we have this new framework that allows us to couple really detailed process models and simulate how a resource would optimally bid into the market, and couple that with actual simulation of the market. And we can do this in a rolling horizon framework. And this is starting to produce some evidence that the price taker assumption is not always valid. So finally, I want to talk about the IDEAS project. So as part of the IDEAS project, we've implemented this framework to capture the resource grid interactions. This is another part of the IDEAS team that works on very detailed dynamic modeling, optimization, and control of various energy systems, both thermal generators, new technologies, hybrid systems. And this can also include conceptual design and actually validation of these models. And what we want to do is couple these capabilities with the ability to simulate both the grid, both expansion planning and the cost production model. And we want to have two new capabilities from the IDEAS project. The first is to be able to understand how changes of the dynamics at the detailed level. We're going to propagate through to the ability to track resources and how to bid, and then market outcomes. And then also being able to take expansion planning results to understand what's needed by the future electric grid under various renewable or CO2 policy scenarios, and then be able to tie that to what types of energy systems are needed and what's the best way to design energy systems. With that, I'd like to acknowledge all my collaborators on the IDEAS project. Everyone shown in blue is part of these grid modeling efforts. And with that, I would be happy to answer questions.
Okay, great. Thank you. Let's thank Professor Dowling for that keynote talk. We've got about 5 minutes here to field some questions. And you can go ahead and add them to the the Q&A box. And I'm just going to go ahead and read them off, and Alex can tackle the question. So the first one it says, have a question about self-scheduling. Does the power plant completely independently decide on its power output, only knowing the price?
Yeah, so in self-scheduling, that's the idea. And it doesn't even know the price. It's just forecasting what the price will be. So it's kind of saying, here's what I'm going to do, and I'm at the will of whatever the market price is. In contrast with bidding, what a resource does is say, for these different price out scenarios, I'm willing to produce this much power. I'm willing to consume this much power. So the idea with bidding is you're kind of you're communicating like a recourse policy, or you're communicating how you, as a resource, you'd want to respond to uncertainty, and that's why it's a lot more robust.
Any other questions? So I've got a question for you. So you showed that it looked like there was a 4% improvement in kind of the outcomes. I don't really have a good sense of what that really means per se in terms of the cost and can you elaborate on that a little bit?
Yeah, so this is simulating a coal power plant that's kind of in this artificial data set that roughly mimics the Southwest US. So a 4% increase in revenue for a power plant could actually be the difference between bankruptcy or continuing. But I want to point out that was actually driven by the fact that small changes in the bidding policy were increasing and causing these price spikes. So I think the more important part of that case study was this price taker assumption isn't really valid, but this framework that we have that co-simulates how the resource would optimally bid, how the market would then clear, and then how the resource would track those market signals, that can actually go beyond the price taker assumption. So we kind of show in this case study that these new capabilities are actually really important. Does that answer your question?
Yeah, that's great. Thank you. There's another question here. So how do you see this analysis extending to the ancillary market or for resources which participate in both energy and ancillary markets?
That is a great question. That's actually something that's on the roadmap for next year for this project. We've independently, as part of the IDEAS team, have extended prescient to consider ancillary services. And then my group in some other work has looked at ancillary services under a price taker assumption. And what we see for ancillary services under a price taker assumption is that's really where you can make the money. So the next step is kind of to modify the bidding formulation and modify the tracking formulation to accommodate ancillary services, and then kind of stitching together all the pieces in that co-simulation framework.
Okay, great. Any other questions out there from the audience? Okay, going once, going twice. All right, well, let's go ahead and thank Professor Dowling for his wonderful keynote presentation. So, oh, looks like there is one more. Do you want to take one more question?
Yeah.
Yeah.
Can you please comment on to what extent ancillary service market is currently being monetized? So there's a lot of resources that actually absolutely depend on bidding into the ancillary service market. And there's actually a lot of literature that shows if you have energy storage, like a battery, so we've done some work. If you have energy storage for a battery and you try to just play in the wholesale day-ahead market, it's going to take 60 years to pay off investment for like a Tesla battery that you could buy today. If you bid in both ancillary services and the real-time market, you could maybe cut that down to 2 or 3 years. So a lot of grid scale energy storage kind of requires either government subsidies, government policies, or ancillary services if they're going to even break even.
Okay, great. Thank you. All right, so we're just about out of time for questions. Now we're going to enter in the last part of this this session after the keynote, and this is really where all of the rest of the 22 talks that we have for this RI session. These were all the videos that have been uploaded, 3-minute videos, and they're stitched together so they will play back to back. This last part of the session does not have any Q&A, of course, and I do encourage attendees to visit the following session from 11 to 11:45, and the individual authors of all the talks here will be in their Zoom rooms to answer questions, and they'll probably have some additional slides or videos to show, so it's very interactive, just like the poster session that we have. And then also I want to remind everybody that Professor Dubasi is going to be sending, again, links for the essentially two awards. One is the RI People's Choice Award and the Hugo Shuck Award. So look at your chat and you'll see those links. All right, I'm going to go ahead and play these videos back to back and enjoy, and we'll see you at the interactive session starting at 11 o'clock after this next hour. Here you go.
Hello, and thank you for listening to this presentation where I will be talking about optimal battery dispatch and real-time state of charge tracking for microgrid applications. My name is Amir Valibegi, and this work is presented as part of my PhD work at the University of California, San Diego, under supervision of Dr. Raymond Colifant. So the problem we are studying involves a grid-connected microgrid where energy storage and PV generation resources are connected in a DC-coupled setup to a microgrid of a medical facility and supply part of its load. The rest of the load is being supplied by the main electricity grid. The objective is to perform subsequent control of power flow at the point of common coupling of the microgrid with the main grid, as well as the state of charge tracking of the optimal battery profile. We also want to reduce the power flow fluctuations at the point of common coupling. The challenge that we faced is mainly due to the unexpected measurement latencies that result from the network communication setup, as there are multiple sensors that are spread across the microgrid and communicate via a network setup. So a summary of the solution workflow is presented in this slide, where there are 3 main steps of number 1, modeling the energy storage and inverter performance using the input excitations that are applied to the energy storage system and measuring the outputs. So we basically aim to get a gray box model of the power flow out of the energy storage and PV system by measuring the outputs and using system identification techniques. The second step involves design of a Kalman filter, where the goal is by using some output measurements, we try to estimate and reconstruct the output using a Kalman filter. And in the case of any latencies or measurement errors, we are able to detect those errors using the Kalman filter and reconstruct the outputs using this filter so that our control performance is not jeopardized. And the third step is the step of control, where we aim to implement the real-time controller. A summary of the sample results over 24 hours of microgrid operation shows the tracking of state of charge and power flow disturbance attenuation. Despite the fact that some measurements are erroneous at parts of these 24 hours, the system is still showing a satisfactory performance. For more details on this, please refer to the actual manuscript. And for any questions, please contact me using the email address provided below. Thank you very much.
Hello. Our paper is talking about filter-based controller to improve the power quality of single-phase grid-connected inverter. In literature, improving the power quality of local low voltage or injecting current to the grid has been studied well. The challenge is how we can improve the power quality of the local load voltage while injecting clean current to the grid. In our work, we designed a controller based on filter-based control schemes to achieve these control objectives and to overcome the cascaded control approach disadvantage. Also, our approach ensures standalone and grid-connected the transition mode without changing the control structure. For the single-phase grid-connected inverter with LC filter, we have a third-order dynamic equation, I1 V out I2. In our approach, we have to find the second-order dynamic system V out in terms of the output voltage, as follows. We have two control objectives, a voltage control objective and current control objective. For voltage control objective, we have to design the duty ratio to ensure the output voltage tracking the reference voltage. And for the current control objective, we have to design the V out reference to ensure the grid current tracking the reference current. Based on the following error signals, and motivated by the stability analysis, we can obtain our control signals. The instantaneous circuit dynamics of the system and the control algorithms have been implemented on the Plex software by using following parameters. For the simulation results, for steady state simulation, we can see from this figures the voltage objective and current objective have been met. For transient state simulation, we can see from this figure that the proposed controller is robust for operating point change. Also, for the transition between standalone and the grid-connected operation, we can see this is a seamless transition between standalone and the grid-connected inverter. In summary, a filter-based control scheme has been designed to simultaneously improve the power quality of the local load voltage while injecting clean current to the grid, and the design based on the second-order dynamic equation in terms of output voltage, and the reliable stability analysis have been used to prove the stability of the closed-loop system.
Hello, my name is Nathan Deline. I'm a PhD candidate in electrical engineering at the University of Southern California, and today I'll be discussing work completed with my advisor, Professor Rahul Jain. I'll be discussing an electricity market which incorporates the risk preferences of a social planner with regard to renewable generation. Our electricity market consists of N thermal generators, a collection of loads with overall demand D, an independent system operator, which plays the role of the social planner, who we also assume has access to a renewable generator with random output governed by F sub W. The ISO can schedule the thermal generators to produce levels X sub 1 through X sub n prior to realization of the renewable generator, following which it may schedule production levels Z sub 1 through Z sub n to make up any shortfall in meeting the demand. Given the social planner's first and second stage dispatch decisions, as well as renewable generation level W, we have the following cost of production across both stages of the market. The ISO's problem is to optimize the expected cost of production subject to supply and demand balance constraints, as well as constraints following from the parameters of the power grid. The issue with this approach is that the realization of a random variable can be significantly different from its expectation, and the real-world observation that economic decision makers tend to be risk-averse. Therefore, in this work, we replace expectation with a risk measure rho and study the risk-aware economic dispatch problem. In particular, in this work, we focus on a risk measure derived from conditional value at risk, or CVAR. The alpha value at risk for random losses Z is the value which will not be exceeded with probability alpha. CVAR is then the expected value of Z, given that it exceeds the alpha value at risk. Our risk measure is a weighted combination of expectation and the alpha CVAR. Note that epsilon equal to 0 recovers the case where we optimize the expectation of total cost, or the risk neutral case. In previous work, when the planner was risk neutral, we established the existence of a sequential competitive equilibrium, a set of production quantities as well as prices such that each generator attempting to optimize its own profits and expectation would choose to produce levels X sub I and Z sub I given prices P1 and P2. These quantities would combine to give balance in supply and demand in both stages. Also, sequential competitive equilibria would always give optimal solutions to the risk-neutral social planner's problem. A central question of this work is whether such a sequential competitive equilibrium exists, given that the planner is risk-averse. The contributions of this work are as follows. We formulate a risk-aware two-stage economic dispatch problem which includes a risk-averse social planner and multiple risk-neutral thermal generators. Despite this discrepancy in attitude towards risk, a sequential competitive equilibrium is shown to exist, and such equilibria are shown to contain optimal solutions to the centralized risk-aware problem. Equilibrium prices directly reflect the ISO's attitude towards risk, and assuming non-strategic behavior on the part of the generators, we are able to specify a mechanism which implements these sequential equilibria. Thank you, and I look forward to further discussing this work in the interactive session to follow.
Hello. Our paper talking about self-synchronizing current control for single-stage three-phase grid-connected photovoltaic system. For any grid-connected inverters, the grid information is needed, such as a grid angle, phase angle, and frequency. Typically, the phase-locked loop schemes, PLLs, are used to measure the grid angle and the frequency. PLLs are sensitive to unbalances and disturbances in grid voltage, and using a PLL with such a grid could lead to instability issues. Moreover, PLLs are used to synchronize the inverter to the grid before connection. In our work, the grid angle and frequency are accurately estimated or observed based on the current measurement. Moreover, the maximum power point of the PV panel has been achieved without DC to DC boost converter. Lyapunov stability analysis is used to validate our observer control schemes. The DQ model of the three-phase grid-connected inverter in the estimated reference frame is as follows. Also, the PV DC bus dynamic. We can see from this model, we use the estimated angle instead of the measured angle. The main control objective of our design is to design a current controller without the knowledge of the grid parameters. So we introduce the error signals, these error signals for the current, for the DC bus voltage, and for the angle and the frequency of the grid. And motivated by these error signals and the stability analysis, we can obtain our control signals, duty ratio, and the reference current for the DC bus to make sure the maximum power point of the PV panel, and the observer or estimated law for the grid angle and the frequency. Instantaneous circuit dynamic of the system and the observer control schemes has been implemented on the Plex software. There's some simulation results here. The grid angle and the frequency. This is the convergence of the grid angle and the frequency. And this is the tracking performance of the DC bus voltage and the current.
Hello, my name is Derek Chang, and today I'm presenting work on stochastic resource allocation for electricity distribution network resilience. This is joint work with Dr. Devendra Shalard, Professor Saurabh Amin. The motivation for our work is hurricane-induced outages in electricity distribution networks, as can be seen in these images of damage after Hurricane Maria. Microgrids powered by distributed energy resources can provide partial demand in microgrid islands within DNs before the system recovers, and thus provide emergency power while the DNs are disconnected from bulk power supplies. An important question follows: what placement of DRs results in the most optimal microgrid configuration? We now formulate a two-stage stochastic mixed integer program to address this problem. Consider timeline decisions and modeling considerations where when a storm is imminent, a storm forecast is available from entities such as the National Hurricane Center. The forecast informs a DR allocation decision. The storm lands, a set of component failures occurs, and the storm passes. Then we consider network repairs and DR dispatch over a multi-period horizon. There's a cost associated with a DR allocation decision, as well as period-wise costs corresponding to the cost of lost demand accrued over a set of considered periods. We aim to minimize this cost of lost demand under a DR allocation and failure scenario. The total cost to consider before the hurricane hits is the sum of stage 1 cost and stage 2 cost, in which the stage 2 cost is an expectation over all failure scenarios. We consider distribution over the probable scenarios, and we aim to choose allocation to minimize this total cost. Focus of our work is to then discuss a solution approach for solving the two-stage stochastic mixed integer program. Our approach is to consider this sample average approximation, which involves approximating the expectation over the stage 2 cost as a simple average over the costs associated with a set of randomly sampled scenarios. This approach addresses the primary computational challenge we face, which is that the number of damage outcomes grows exponentially with network size. We implement a solution approach known as L-shaped Benders decomposition to solve the sample average approximation and employ a greedy approach for solving the subproblems. At an iteration of the algorithm, we first solve the master problem and obtain the set of optimal allocations subject to so-called Benders cuts. If the set A star is empty, this means that Benders cuts from previous iterations have rendered the master problem infeasible, and we exit Benders decomposition. If the set is not empty, an allocation is chosen at random for the next step, which is to solve the stage 2 subproblems, one for each damage scenario considered. We use a greedy approach to solve the subproblem, which decreases the subproblem computation time. We then fix the subproblem discrete variables and solve the resulting linear program. These results apply a Benders cut to the master problem at the next iteration. In this slide, we compare our approach to other solution approaches to demonstrate the effectiveness of this approach. These are the approaches considered in order of increasing exhaustiveness and exploring the solution space. This plot, which shows period-wise system performance for a 36-node distribution network, demonstrates that LBD with GAR method and SE has equivalent system performance, where SE considers every possible allocation solution and is thus guaranteed to uncover the optimal solution. Moreover, LBD with GA outperforms the greedy approaches SA and BORA, which less exhaustively search the solution space. This concludes the presentation. Thank you very much, and I look forward to further discussion after the presentations are finished.
Hi, I'm Liang Hao, a PhD candidate at the Chinese University of Hong Kong. It's a work I did with my supervisor, Professor Yun Jianxu. We studied the EV charging scheduling problem with time-varying power capacity. We formulated the problem as rested banded. Playing an arm is equivalent to active a charger. The challenge is how to schedule and hard time-varying processing rate limits. In our problem, the schedule horizon is finite and discretized. The processing cost is CT, and the maximum processing rate is deterministic. The state of job is denoted by X. The action at each stage is a binary vector, and the total number of activated chargers should be less or equal to MT at any stage. This constraint imposes a difficulty on scheduling and sometimes makes optimality not achievable. One of our contributions is the development of the Lagrange index. As shown in this roadmap, first, we introduce time-varying multipliers for Lagrangian relaxation. After decomposition, we solve the relaxed problem by linear programming. Next, in step 3, we fix future multipliers in ARM-I's reverse code as the optimal multipliers to compute the Lagrange index. Another contribution is a randomized tie-breaking rule. A randomized index is defined as follows. Here, V is the Lagrange index. Dirt is a small positive constant. Eta equals the random action in phi star if the state is weighted by phi star. Otherwise, eta equals 0.5. Phi star is the optimal randomized policy we got after solving the relaxed problem. We note that the randomized tie-breaking rule is essential for the asymptotic optimality in some cases. Numerical results show that the improved Lagrange index policy outperforms the classical weighted index policy by 10% to 83%. That's the end of the presentation. Thank you.
All right, let's get started. I'm Yufei Tang, Assistant Professor in the Department of Computer Electrical Engineering and Computer Science at Florida Atlantic University. Today, I'm going to present adaptive super two-string sliding motor control for OCT-driven PMSG. The research background in one sentence is that I'm going to design efficient control method for OCT that can harvest marine renewable energy to powering the blue economy. There are significant challenges. The OCT are complex and involve nonlinear dynamics with strong coupled external marine environmental disturbances and internal parameter uncertainties. So advanced nonlinear control techniques should be designed to meet this challenge, and we're looking for sliding motor control for its robustness against unmodeled dynamics and parameter uncertainty under matching conditions. However, the robustness of SMC is achieved at the cost of high-frequency control signal oscillation known as chattering that cannot be tolerated in generator control. The three ways to reduce the chattering: first, a saturation of signal function, however, with the loss of robustness; second, a high-order sliding model technique, however, with the main challenge related to the high-order time derivatives of the sliding variables; and third, dynamic gains. That is what we are looking for today. The proposed approach is shown in these slides, and the two key equations are shown on the left. And I'm not going to expand the discussion here. I will leave this in the poster session. The key innovation of a proposed approach is that we propose an adaptive gain super two-string algorithm that ensures the sliding model has adaptability while the rate can vary with the current sliding variable. Without overestimating the control gains, the design establishes a real second sliding model in a faster finite time. Compared with these two references, the novelty of the proposed adaptive law is that the gains can adapt both approaching and being on the sliding model. The variable adaptive rate can make the second sliding model established in a faster finite time without overestimating the gains by a switching rule. We have proved the finite time convergency of the closed loop system through a Lyapunov function technique. And we also the simulation studies carried out on a numerical model of 720 kilowatt PMSG-based OCT. And the overall framework is shown here, and we can see that we have the wave current models, the OCT hydrodynamic model, and the PMSG model. They are all detailed dynamic models. We have carried out the simulation to validate the effectiveness of proposed method with two ocean current conditions. And the blue shows our proposed method. We can see that we have super performance compared with the conventional ones. Thank you, and see you in the digital poster session.
Hello, My name is Karim Bardawil. I'm a PhD candidate at the American University of Beirut in the Electrical and Computer Engineering Department. I'll be presenting the following work entitled Applying the Similarity Method on Pacheco's Magic Formula to Estimate the Maximum Longitudinal Tire Road Friction Coefficient, which I co-authored with my advisors, Professor Nassim Daher and Professor Eli Shammas. Tire road friction coefficient dictates the vehicle's behavior, especially at handling limits. Its characteristics are strongly interweaved with automotive active safety control systems. Also, autonomous driving vehicles utilize a priori knowledge of the coefficient for path planning and control. Hence, real-time estimation of the maximum TRF coefficient through reliable and low-cost observation schemes is crucial. There exist two types of estimation schemes in literature: experiment-based methods that require additional hardware and custom sensors, and model-based methods that rely on tire models, wheel, and vehicle dynamics. Both provide medium to high accuracy levels. However, model-based approaches are more appealing in practice. The block diagram of the general estimation scheme shows that the proposed work in blue is built on previous estimation blocks. That's because the estimation of mu relies on estimates of the longitudinal and normal tire forces and tire slip. First, Pacheco's magic formula is fitted using experimental tire data with unity friction surface. Then similarity method is applied to characterize shear forces at conditions different from nominal friction. Iterative solving methods for mu star are avoided in return of obtaining faster solutions with reasonable accuracy. That is done by introducing mu bar. Hence, the unique solution is approximated by the following mu star equation. Next, an adaptation law for the estimate mu hat is used. It guarantees an unbiased estimate when the tire slip and tire forces estimates have converged to their true values. The smooth projection parameter update law is presented in this figure, where convergence speed of the update rule is dictated by gamma. And by choosing the following Lyapunov function, stability and convergence of the estimation are guaranteed. Multiple simulations are conducted to evaluate the performance of the estimator in an accelerate coast brake maneuver. Here we can see the estimator rapidly reacting to the false initial condition and is able to track the maximum TRF coefficient within an acceptable range. The plot here shows the estimate's ability to go from 0.8 to almost track the high step mu 0.9, then promptly reacts to the sudden step change and quickly adapts. Lastly, a split mu change on the left versus right tires is considered to assess the ability of individually estimating the TRF coefficient on both tires independently. When estimates for the maximum TRF on the left tire settle at mu equals 0.5, the split in mu drives the estimator to adapt for the change while it remains constant on the right tire.
Hello, everyone. My name is Bolin Xu. I am an assistant professor in Columbia University. And this work was done during my postdoc at MIT with Magnus, Alden, and Francis. So in this work, we developed a highly efficient algorithm to solve model predictive control for engine storage, to best utilize engine storage fast response speed, and also achieve very low implementation cost, especially for utilizing distributed engine resources. We consider a very general formulation, including a look-ahead period and terminal state cost, power and energy rating, efficiency, and a state-of-charge evolution constraint. Our main technical contribution is applying dual decomposition to solve the engine storage control problem, where we utilize the Lagrangian dual variable associated with the state-of-charge evolution constraint, theta. Once you know the value of theta, it's very easy to obtain the optimal control. While the main challenge here is to find the optimal value of theta. Well, we proved in this paper that theta can be found using a bisection algorithm combined with forward simulation. The algorithm achieves constant space complexity and worst case log linear time complexity with respect to the size of a problem. Here is a quick comparison with a benchmark optimization solver Groovy. In a pretty extreme test case, we consider a piecewise linear objective function with 5,000 segments every 5 minutes. Look ahead horizon. So the Groovy takes several minutes to solve this problem. and the complexity increases superlinearly, where our algorithm solves all the problems less than 0.5 millisecond. Because we consider a model predictive control framework, this algorithm can be very easily applied to different applications, including economic dispatch, electric vehicle charging, and arbitrage. In our current work, we have explored extending this algorithm into multi-stage stochastic control, and also we are working on multi-storage control. If you have questions, feel free to talk to me later or shoot me an email. Thank you.
Hi, this is feature selection for state of charge estimation of lithium iron phosphate versus lithium titanate batteries via electrochemical impedance. This represents work mainly done by Alexis Leroux in collaboration with Peter Weddle, Robert Key, and myself, Tyrone Vincent. The subject of this work relates to estimation of the state of charge of batteries. While batteries can measure the discharge current and then use Coulomb counting to determine changes in their charge state, they need an absolute reference to account for startup or to account for drift due to noise in the integration. Typically, this reference is supplied by the open circuit voltage, which is the voltage of the battery at rest. So here we see an example of this voltage versus state of charge for an LFP versus graphite battery. And there's this distinct one-to-one relationship between the state of charge and voltage. However, this is not true for all batteries. A relatively new type of battery pairs a lithium iron phosphate cathode with a lithium titanate anode. This battery is inherently safe and useful for high power applications. Here we see a plot of the open circuit voltage of this battery. And we see that the response is flat over a large portion of the operating range. And indeed, there's hysteresis depending on whether you arrived at that state by charging or by discharging. So for these types of batteries, we need an alternate reference. One possible reference can be obtained from what is called the electrochemical impedance spectra, which is simply the frequency response of the battery. This type of impedance can be measured during operation using existing hardware. Typically, there are balancing resistors, which are used to discharge some cells in order to ensure that all cells are equally charged after charging. By switching this resistor on and off and measuring the voltage perturbation, the frequency response can be estimated using system identification methods. Here we show the EIS measured on an LFP LTO battery at different states of charge on an Nyquist plot. As is typical in batteries, the y-axis is flipped for the Nyquist plot. As can be observed, the impedance does have significant differences depending on the state of charge, implying one could find a mapping between the EIS and the state of charge. However, we have to determine what features are important and which features can be utilized in order to obtain an accurate prediction. So this work shows that lasso regression is able to find appropriate features, and with appropriate calibration, we see that we are able to quite accurately determine the state of charge from EIS measurements. The details of this work are available in the poster. And I'd just like to also acknowledge support from ONR and assistance from K2 Energy for this work.
I apologize, but I think this video that was uploaded did not have any sound. So we're just going to have to sit through this one without any sound. Every now and again, there are videos that uploaded to the system that didn't have sound.
So we do have a People's Choice Award for these RI presentations for each of these groups. So if you nominate them, it's available till noon today, Denver time. And so kindly take a look at the ones you liked, and maybe you can also have a chance to visit the live presentations from 11 to 11:45. And if you like them, do consider nominating them. And I'm going to send the link again just now. So.
The other thing I want to remind everybody about is also, and I noted in my chat, all these videos have been uploaded to the Paper Plaza system, the online conference program. So feel free to download those and view them later again.
Hello, today I'm going to discuss the effects of mechanical damage on the electrical response of lithium-ion pouch cells. In this study, we use electrochemical impedance spectroscopy in a distributed equivalent circuit model to determine trend of changes in the cell parameters related to mechanical damage. To give context to the picture on the right, it shows an electric vehicle tested by NHTSA. This car was thought to be safe for storage, yet it caught fire and destroyed the surrounding vehicles. This shows just one example of how important it is to determine the safety status of lithium-ion batteries. Now we're going to discuss the need for accurate modeling. State of health estimations determine the current state of a lithium-ion battery. It characterizes the degradation of cells after electrical cycling and use in various environments. This is currently done utilizing capacity fade and internal resistance. A key contribution of this study addresses the lack of literature in pre-failure mechanical damages. Recent studies suggest a critical depth of deformation that causes an electrical short. Yet microfractures in the electrical coating and thinning in the battery separator occurs prior to an electrical short, and we aim to relate the mechanical deformations to electrochemical processes prior to electrical shorts. This brings us to pre-failure detection and mechanical damage in lithium-ion pouch cells. Currently, in the automotive industry, there is no reliable battery safety characterization method, and battery packs are scrapped when minor accidents occur. The two experiments in this study include step indentation and charge-discharge cycling following hemispherical punch. The mechanical damage applied to the cells in this study is 57 millimeter hemispherical punch. We collected EIS data and modeled the cells using a distributed equivalent circuit model. This model can be seen here in the third box to the right. Data analysis was performed to determine the trend of changes in the ECM parameters due to controlled mechanical damage. The step indentation experiment and modeling showed that some of the ECM parameters diverge from the controlled cells after a certain indentation depth. An example of this is in the charge transfer resistance. At 3.2 millimeters, it can be seen that a rapid change occurs. This is shown in the figure in the bottom right-hand corner of this slide. Trend changes suggest a promising direction in detecting pre-failure mechanical damage using EIS measurements and ECM parameters. This study is the first step to gain key insights in pre-failure mechanisms in lithium-ion cells, which can lead to major contributions in safe battery usage. Further detail can be found in our paper 1265, along with a
Apologies again. I think this is also another video that doesn't have sound. I do want to remind you that you can look on the online program. Sometimes the downloaded videos or that play through the program itself has sound. But unfortunately, when we had downloaded them directly through the system, some of the videos, not very many, but just a few, lack sound.
And also they'll have a live presentation in about at the end of this session at 11 o'clock. Yeah.
Sorry about that. And one other thing is we just posted a notice on the chat. The poll for the People's Choice Award will close at noon. for this RI session. And so you'll have a little bit of time, of course, to go and visit the authors directly in the individual Zoom rooms to ask further questions. So you'll have up until noon to make your selection.
Also, please copy that link because it goes away after the chat session is closes for this session. So if you want to, for example, nominate some other time, a little bit later. So.
Road traffic injuries have caused 1.35 million fatalities globally in the year 2016. Despite the small vehicle population of heavy commercial road vehicles, they were involved in 32% of fatal accidents in India. Active vehicle safety systems, such as an anti-lock braking system, can potentially reduce these fatalities. Wheel slip regulation is an integral part of an ABS algorithm, but for that, first we need to understand what the wheel slip is. It is defined in equation 1, and its relationship with the road friction coefficient is depicted in the B-lambda curve. When the wheel slip crosses the peak slip, the wheels lock, and that can potentially lead to an accident. Wheel slip regulation prevents wheels from locking and reduces the braking distance. However, it requires the reference wheel slip for regulation, and this reference wheel slip changes with the road surface, which is unknown. So based on wheel slip regulation tests, we observed that there exists some value of wheel slip variance corresponding to optimal reference slip. This became the foundation of the proposed optimal reference slip algorithm. It essentially identifies the tire road interface by estimating the corresponding reference wheel slip. It was developed as a dynamically weighed, multi-objective, least squares optimization problem. The dynamic weighing scheme was based on the past wheel slip feedback. This algorithm was integrated into a hierarchical control framework. It has an apply exhaust logic for wheel slip regulation and a PID-based delay compensation element for improved actuator response. This framework was validated on a hardware-in-loop setup involving a pneumatic brake system of a 16-ton vehicle. The developed ABS algorithm was tested for an unladen heavy commercial road vehicle for varied speed and road conditions. The algorithm was found to be correctly identifying the reference wheel slip. As depicted in figure 5, the reference slip starts from the same initial condition, but appropriately converges to the corresponding reference slip of low friction and high friction surfaces respectively. In the table, we can observe a reduction in braking distance in all the braking scenarios. Additionally, it can perform even on split friction surfaces and during surface transition. So in conclusion, the optimal reference slip algorithm can estimate the reference wheel slip for any road surface in real time and prevent the wheel lock.
The video you just saw was of a NASCAR we adapted to be controlled by a person with quadriplegia. Steering is controlled by tracking head position with respect to the car. We do this two ways. First, we have a gyro attached to the head and a gyro attached to the car. We combine this information to get a high rate head orientation with respect to the car. Second, we track the head using a camera at lower rate. The two orientations are then mixed together via Kalman filtering techniques.
We designed and fabricated a custom helmet visor with specifically known glyph locations that are easy to lock onto with vision processing.
There are many elements or tasks that make up the head control system. These tasks must run simultaneously and in tight synchronization. We designed a multi-threaded system architecture running on an NVIDIA TX2 computer to seamlessly handle all of the control and image processing aspects of the race car.
Hello, my name is Jiun Han from the Argonne National Lab. Today I want to talk about a real-time energy optimal speed planner and its energy impact. Eco-driving control aims to minimize fuel or energy consumption by controlling the speed through automation and connectivity technology. To design the eco-driving controller, we should think about the three main perspectives: energy optimality, computing complexity, and robustness. We want to achieve the global optimum, but if we only focus on the energy optimality, computing complexity is likely increase. Furthermore, for the various scenarios, the controller should provide a consistent energy saving potential without any issues. By balancing these three perspectives, we propose the real-time implementable speed planner. So we prioritize the implementability, which means that we simplify the energy optimal control problem and derive the closed-form solutions as a function of the boundary conditions. Then we add the complexity in order to handle the unconsidered factors, for example, the change of the speed limit showing the red line in the middle figure. The proposed speed planner selects the one of the modes showing the orange line in the middle figure and adjusts the boundary conditions, and then use the closed-form solutions to compute the energy optimal trajectory for the given mode. The last step is tuning the speed planner for the high maturity level. So we use high-fidelity simulation framework called Roadrunner to quantify the energy-saving potentials. We describe the SOLTI-8 real-world route scenarios from the here maps data. So consider the two electric vehicles and set the different penetration rates depending on which model is used for each vehicle. So human as a baseline indicating the 0, and as a CAVs, the connectivity ACC and connectivity echo driving indicating the 1. And these three figures shows the energy savings and the travel time savings with respect to the baseline case for the mixed and suburban and urban road types. So different colors indicates the individual road results. So as going from the mixed to the urban road type, and as the penetration rates increases, the energy saving is shown to increase. As a CAVs, the proposed planner CXO leads the greatest savings up to 12.6% in average in urban routes. So key takeaway here is that CAVs can reduce the travel time and also save energy more. In this work, we presented and validated a real-time implementable speed planner. So future works would be a fine-tuning the speed planner. Thank you so much.
Good morning. My name is Pingyun Chen. Today I'm going to discuss research on design of cylinder deactivation control framework for gasoline engine without valve deactivation. The objective of this study is to design cylinder deactivation control framework for gasoline engine without valve deactivation mechanism, quantifying fuel saving benefit from cylinder deactivation, evaluate engine smoothness when cylinders are deactivated, design emission control strategy to support cylinder deactivation. The test platform for this study is a Toyota 23RFE V6 3.5 liter gasoline engine. The engine control system is developed based on DiskSpace Micro AutoBox and RapidPro. This is a snapshot of this engine platform. The cylinder deactivation control framework aims to produce the same amount of engine power with different numbers of active cylinders while still maintaining the engine smoothness. Our engine deactivation control framework consists of 2 stages. The first stage is adaptive engine speed control. The second stage is the throttle body control. The figure on the lower left shows the engine speed at different number of active cylinders. The 6-cylinder operations versus 3 cylinders operations. As we can see from this figure, engine speed is controlled at a very narrow bound. And we can also observe that the engine fuel consumption has been reduced significantly by 25% at 2000 RPM. We also observe that as engine speed decreases, the fuel saving benefit is decreased as well. Since no valve is deactivated for deactivated banks, the air is pumped through to the exhaust gas. To address emission control issues, we deploy 2-stage emission control. The first stage is to remove NOx and the cross couple by controlling the active bank lambda at 0.99. The second stage is to reduce the CO and hydrocarbon emissions in the overall lean condition. With the 2-stage controller, low NOx, hydrocarbon, and CO emissions can be accomplished. Thank you for your attention.
Hello, ladies and gentlemen. My name is Kuo Yang. I'm a PhD candidate from Tennessee Tech University. This paper is co-authored by my supervisor, Dr. Pian Chen. It is about the ammonia distribution control for a 2-cell SCR system in a new configuration. The paper is motivated by the existing problems in the conventional system. The first issue is the slow recovery process, which are due to the slow dynamic in the SCR system, and also the certain sequence that the conventional system has to follow during the transition process. The second issue is about the robustness of the ammonia storage profile, which are due to the inevitable ammonia slip from the upstream cell to the downstream cell, and also the lack of the control in the downstream cell. The new configuration of the proposed system is to add a flow duct bypass part of the raw exhaust directly to the downstream cell. With the 2 sliding mode controllers, both cells can get individual controls. The injection rate of the urea solution is designed to control the upstream cell, and the split ratio of the valve is designed to control the downstream cell. With this characteristic, the proposed system is able to conduct a fast mode transition and also get better robustness at the ideal profile. 2 cases are used to validate the proposed system under WeA06. In transition A, the proposed system is able to complete the transition from the initial profile to the ideal profile faster. It shows better robustness at the ideal profile comparing to the conventional system. In the transition B, the proposed system is able to complete the transition process in 400 seconds, while the conventional system is unable to complete the same transition process in the 600 seconds simulation. For further details, please check out our paper, and we're looking forward to further discussions in the interactive session. Thank you.
Hello everyone, my name is Paul Padilla. I am from Eindhoven University of Technology, and the topic that I am presenting today is a Port Hamiltonian approach to complete vehicle energy management. This is a joint work with my colleagues Juan Flores and Thijs Donker. Electrification of the automotive sector has become an important tool to reduce CO2 emissions. Logically, this can only be achieved if this technology is fully adopted in the market. Unfortunately, to arrive to this point, we still have to overcome several problems. For instance, range anxiety. One way to mitigate this issue is to reduce energy consumption by means of energy-efficient operation. This implies the design and implementation of energy management strategies which are obtained as solutions to optimal control problems. Power-based approaches are commonly used to formulate energy management problems. To have a better insight, let's consider the case of an electric vehicle where the power is transported from the battery to the driveline to satisfy a power balance that considers the mechanical braking and a given power request. More elements can be considered in the design. The main goal is to find the optimal way to distribute power among all the subsystems. This formulation is completely given in terms of power, which might be a disadvantage if constraints on physical variables like current or torque are required in the energy management problem. Port-based approaches are an alternative that consider physical variables in the problem formulation. In this case, power flows are described in terms of conjugated variables at each port of the subsystems. For instance, voltage and current for the battery or angular velocity and torque in the electric machine. The difference between these approaches lies in the way that the subsystems are represented. For power-based representations, each subsystem contains a buffer that stores energy and a converter that describes the power consumed. It is clear to see that the energy extracted from the subsystem is less than the energy originally stored. A Port Hamiltonian representation introduces the concept of energy losses and internal energy. When energy is transported from the input port to the output port in the subsystem, part of it stays stored internally. Another fraction is dissipated. To be more precise, in a power-based representation, the energy buffer is normally described as a linear dynamical system, and the converter is described as static quadratic nonlinearity. In the Port Hamiltonian case, subsystems are completely described by this specific linear dynamical representation. Moreover, the internal energy and energy losses are derived directly from the parameters of this representation. Note that this does not happen for the power-based case, where the converter and buffer are often considered independent entities. Therefore, the main advantage of a Port Hamiltonian representation is that it unifies the concepts of energy buffers and power converters in a single dynamical system. As a consequence, it is possible to systematically formulate physically insightful decomposable optimal control problems. In summary, this paper proposes an alternative modeling framework based on interconnected Port Hamiltonian systems for energy management applications.
Hi, my name is Han Yang. I'm a PhD candidate in mechanical engineering at the University of Michigan. Our work here develops an efficient uncertainty quantification method using generalized polynomial chaos for online simulations of automotive propulsion systems. With many subsystems, automotive propulsion systems are inherently nonlinear and can be very complex. Coupled with significant uncertainties in real-world conditions, control and decision-making is a challenge. Current approaches have limited adaptivity and often rely on ad hoc rules and careful calibrations to handle uncertainties. With the increasing level of connectivity, data, and onboard computational capacity in future vehicles, there's a great opportunity to develop online simulations that can forecast system behavior on uncertainty and enable proactive control and decision-making. In order to achieve useful online simulations, one needs to account for multiple sources of uncertainty. With all these uncertainties, the simulation essentially becomes a stochastic one, the evaluation of which can be too expensive for online applications. Therefore, an efficient uncertainty quantification, or UQ method, is required to enable such online simulations. To achieve that goal, we employ a technique called generalized polynomial chaos, or GPC. GPC utilizes polynomial approximation to decompose the stochastic system, essentially into two parts. The first part contains the deterministic part of dynamics, Xi. The second part contains the uncertainties or randomness which reside in a set of orthogonal polynomials phi. We can then reconstruct the equation motion using stochastic Gherkin projection and find the dynamics of the deterministic expansion coefficients Xi. The takeaway point is that only this deterministic dynamics is required to be computed on the fly. There's no need to sample, which greatly reduces the computational complexity for online simulations. To demonstrate the performance of this approach, we use the following drivetrain model in a torque-based simulation for 1-2 upshift. The model has 4 states, 2 inputs, a nonlinear torque converter, and considers 4 sources of uncertainties, which are listed on the right. We benchmark our method with the standard Monte Carlo algorithm. In the plot on the left, the horizontal axis is the computational complexity measured in floating point operations per time step, and the vertical axis is the root mean square error of the estimated mean values for each of the 4 states. The GPC curves reside significantly lower on the plot compared to Monte Carlo, indicating that for our system, GPC is at least 2 orders of magnitude more efficient. Besides this significant computational efficiency benefit, the proposed approach also readily enables variance-based global sensitivity analysis via Sobel indices. An example of this analysis is shown on the right. This enables sensitivity analysis with minimal additional computational cost and provides insight into the effect of each uncertainty source in real time. With that, I look forward to discussing more of our work with you in detail in the following interactive session. Thank you very much.
Good morning. Today I'll present our paper titled Online Parameter Estimation for Human Driver Behavior Prediction. Driver models are crucial for planning in autonomous vehicles, as well as validating their safety in simulation. Highly parameterized black box driver models learned from data are very expressive but lack safety guarantees as well as interpretability. On the other hand, rule-based models are interpretable and can be designed to guarantee safety but are less expressive. In this paper, we try to combine the best of both worlds by learning the parameters of rule-based driving models from driving demonstration data. The video on the right shows our objectives. The green vehicles represent recorded driving data. Suppose we are trying to model the driving of one of these vehicles shown in white. Our driver model is shown by the blue vehicle. We want the driving behavior of the blue vehicle to match that of the white vehicle. Further, the driving behavior also needs to be safe and realistic in terms of the overall traffic flow. The rule-based part of our driver model consists of the stochastic intelligent driver model for lane following and the stochastic mobile model for lane changing. We use driving demonstration data to estimate the parameter of these rule-based models in an online fashion using Bayesian estimation. The hidden state contains the parameter of the rule-based models, and the observations are the position traces of the vehicles being observed. We solve this Bayesian estimation problem using particle filtering as shown in the figure on the right. We use the NGSIM Highway 101 dataset. We randomly sample an initial scene configuration from the dataset and replace 20 vehicles with vehicles driven by our driver models, as shown by the picture on the right. We simulate the scene forward for 50 time steps and extract metrics that capture prediction performance as well as global traffic phenomena. We compare our driver models against both rule-based and data-driven benchmarks. In the figures shown here, default represents the IDM model with parameters published in the literature. Nonlinear fit represents IDM models with parameters extracted using nonlinear least squares fit. Generative adversarial imitation learning, GALE, represents a black box driver model that uses deep reinforcement learning. The figure on the left shows the root mean square error in the speed of the vehicles over the simulation time horizon. Our model outperforms the others by showing the lowest RMSE. The figure on the right shows the number of undesirable incidents such as collisions and off-the-road driving. The drawback of the black box model becomes apparent here. Rule-based models do not show such undesirable behavior, thereby highlighting their safety. The video on the right shows a congested scenario from the NGSIM dataset, where the blue vehicles are all driven by our driver models. It's great to see that we see no collisions at all. In conclusion, we used particle filtering to perform recursive Bayesian estimation to learn parameters of the rule-based models online from driving demonstration data. We demonstrated these driver models on NGSIM data, and we look forward to your questions during the interactive session. Thank you.
Okay, thank you for attending this rapid interactive session. We've shown 22 talks, and now the authors will be going to their respective Zoom rooms and interacting with attendees and further showing maybe slides or videos to talk about their research. Thank you very much and have a wonderful day. And we'll continue again tomorrow and Friday with interactive talks. And of course, in the afternoon, we've got the standard technical sessions with the 15-minute talks. Thank you very much.